Hello. Last time we looked at how you do pre-processing in the full threshold case, and the time before that we looked at pre-processing in the Q2 access structure case, and this time we're going to put it all together to give us a final algorithm to do a multi-party computation. Remember, the pre-processing goals are to produce multiplication triples, square pairs, bits, and these input tuples. We've already seen that the input tuples are in some sense already correct, because if you kind of lie with the input tuples then you're basically only screwing over yourself, so there's no point in checking those. But what we've so far presented is only a passively secure algorithm for multiplication triples, square pairs and bits. So now what we have to do is turn those passively secure protocols into actively secure ones, and to do that we're going to use a process called sacrificing. What sacrificing does is it takes, for example, two multiplication triples and uses one to check the other. If both are correct, the test passes, whereas if one of them is incorrect, the test fails. The result being is that you basically burn one of the triples to test the other. So you have these two triples, you throw what you do this algorithm called sacrificing, and then you throw one of the triples away. And the reason you have to throw one of the triples away is because sacrificing reveals information. So what we do is we're going to take a triple ABC and we're going to burn another triple FGH so as to check it. In the case of squares, we're going to take a square pair AB and then we're going to burn another square pair FH to check it. Bits are slightly different in that to check a bit, what we actually do is we burn a square pair. So that's a slightly different thing. So we have a triple ABC and a triple FGH. We want to check that C is equal to A times B, and in some sense that H is equal to F times G. So we first pick a value T that's known to all players. So if we just exchange committed values, open them, and then kind of use the XOR of all those exchanged committed values to see the random number generator to get T. Now what we do is we compute rho, which is T times A minus F, and we open it. We just open it but not the map value or whatever. So this gives us that if F is, we can think of F as a key and it encrypts T times A. So F is like a one-time pad encryption key. We do the same with B minus G. So B is encrypted by the one-time pad key G. And now we look at this expression E. Now, if C is equal to A times B and H is equal to F times G, in other words everything's fine, then E will evaluate to 0. However, if C is not equal to A times B or H is not equal to F times G, then the probability that E is equal to 0 is actually 1 over P. And why is this? It's because the probability is conditioned on this random number T, which has been chosen independent of the triple that we're checking. Okay, so with very, very high probability, if the values are not correct, then E will not be 0 and we will reject. But if with high probability, if the values are correct, we will accept and carry on. So this turns a passively secure triple production protocol into an actively secure one for very little extra cost. Square pairs is done almost exactly the same. We construct an equation which evaluates to 0 in the same way, slightly cheaper. And bit sacrificing is the same. We kind of do it the same. And here we're essentially using the value that if you've got a bit, here we're essentially using the property that if you've got a bit B, then B squared is equal to B, because 0 squared is equal to 0 and 1 squared is equal to 1, and that's kind of the only things that have this property in the finite field. Of course, when we do this, we have to check the openings have been correct. So for example here, that we check that this opening of this row is correct. For Q2 access structures, we do this via the hash check. If we're not doing a full communication round, we're doing a reduced form of communication, we do this by using the hash check, which we described way back. Or we use the map check, which we also described way back, to check that those values are opened correctly. So checking the openings is easy as well. So now we have a fully actively secure offline phase. So we can now move to the interesting thing, which is the online phase. And it turns out now everything's easy. So we've got these triples we've produced, and we want to create this react. We've got a way of checking values, we've got a way of producing these triples and this other pre-processed data, and now we just want to perform reactive MPC computation. This is easy, and all we're going to really do now is just focus on multiplication and input output, because everything else is essentially an optimization of that. So for multiplication, we use this beaver multiplication trick. We want to multiply x and y. We take a triple off the triple list. We execute this beaver multiplication trick, and this will give us the multiplication. We have to check that when we open the epsilon delta, that we've got a valid opening, which we do. We're using this either the hash check or the MAC check, depending on whether we're in Q2 or full threshold. And then we get a beaver multiplication algorithm. And it works because if we look at what that z was here, and we expand it out, boom, 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 we get that z is equal to xy. And there's nothing really going on here. Now there are various, this is not the only way of doing online multiplication. There are various ways of doing this. In fact, you could actually get rid of the pre-processing for the Q2 access structure, and you could actually do a Maurer style multiplication in the online phase and check it with some other mechanism. However, the reason we prefer doing it like this is that this gives us the fastest online computation for multiplication, as opposed to maybe the fastest total computation when you take into account pre-processing and online computation. If you're interested in a system where you kind of want to maximize your performance in the online phase, then this is the way to go. So that's how we do multiplication. Inputting of data is kind of cool. We take one of these input values that we've computed for player I. If player I wants to enter a secret value x, he just broadcasts the value x minus r because he knows the value r, and then all players can locally compute the sharing of the value x because they take this value of x minus r that he's just broadcast, and onto it they just add their value of the sharing of r that's been pre-shared in the pre-processing phase. No, we can't protect against someone lying and inputting a wrong value because it's their input value. You know, we don't protect against lying in MPC. Output of data works in kind of the opposite way. If we want to output data to one player, that player I. So all players, if we want to output, say for example, x to player I, all players compute the sharing of x plus r for one of these input tuples. We now open and check the value epsilon, open it, and then check whether it's max correct, check whether it's consistently been opened correctly. And then given that this is basically now a one-time pad encryption of x plus r, the designated player can extract x because he knows r. So that's kind of nice and easy there. And that's it. How easy can it be? So what is this? What is the things that we've done? We can compute linear functions for free, as we have a linear secret sharing screen. We can open data and verify its correctness in all sorts of different efficient ways, because using this hash check or the MAC check protocol, depending on whether we're in a Q2 or a full threshold access structure. We can compute multiplications using the pre-processed beaver triples, and we can input and output data because we have these pre-processed input triples. And because of that, we can therefore compute any function securely, because we can write any function as a sequence of additions and multiplications. And that's it. From the point of view of just being able to theoretically execute any function securely, we can now do it. The next question is optimizations, ways of processing data in a more complex manner, more complex data types, etc., etc. And that's where these shared bits come in. So that's where it gets much more advanced. But the basic technology is simple when you boil down to it. So that was it. That was a description of how you do linear secret sharing based MPC. We might come back and revisit this in future installments. But for now, you've got the basic idea, and you can go off and do calculations securely using linear secret sharing based MPC.